Gentlemen, welcome back. Sorry for the very long hiatus. It's been about 5 or 6 months since I posted a video. I was running a hyperscale data center project in another state and got divorced in the middle of that. So I've been a little busy, terribly sorry. We're gonna jump right back in. Before we get too far along, there is more background information that you need to know about relays and how they operate and how they think before we can just jump in and start testing them. Today we're gonna cover Boolean algebra or Boolean logic equation, digital binary logic in general, some ANSI device code numbers because those are absolutely critical, as well as an introduction to the SEL logic equations that we're gonna be dealing with throughout the rest of this series and probably many more videos that I make in the future. All of these are gonna combine to make the concrete foundation of protection relay testing. This is very, very important before we get started. You need to know what the relay is trying to do with the settings that are in it and how it's programmed. We're gonna jump right into Boolean logic. It's named after, of course, a famous 19th century white guy. Boolean logic, or Boolean algebra, is a system of mathematical functions using binary zeros and ones that's often associated with basic computer processes. To briefly summarize the Wikipedia page, elementary algebra, the math that we learn in school as kids, uses base 10 numbers and has 4 main operations: addition, subtraction, multiplication, and division. Boolean algebra has 4 common operations as well, but they're AND, OR, NOT, and XOR, or exclusive OR. And the variables can only be 1 or 0. It's base 2, right? There's only 2 options that any number can be. I'll put the graphic up. There are little symbols that you can draw to help track these Boolean operations on paper for more complex equations. You can put these AND or operators in strings to do some very convoluted things. In fact, transistors set up like this, they work in AND or operations. That's literally how computers work. That's how the processor in your computer works, by comparing these AND or functions billions and billions of times. If you're familiar at all with coding, you can think of these as if-then statements. AND just means if X and Y are true, then the output is true. Or obviously means if X or Y are true, then the output is true. Anytime you hear true, just assume that the output is a digital 1, or the bit is high. Anytime you hear false, well, that would be 0. The bit is held low, and it's not true. The third operation is called NOT, which basically just reverses the input. If the input is high, NOT brings the input low, or a 0, and vice versa. Lastly, XOR, or exclusive OR, it's only true if X or Y are true, but not both of them. There's, of course, other shortcuts that are just shorthand for different combinations of these operations. It might be a little bit hard to remember at first if you're coming from this fresh, so you can screenshot the little chart that I've got up on screen, or look up Boolean logic and just read the Wikipedia page for a refresher every time you need it. Okay, I hope that makes enough sense, but it's not very useful by itself. Just a bunch of 1s and 0s and ANDs and ORs. That doesn't tell us a whole lot. We need binary variables that can change state so we can do something with those logic equations. In most relays, each protection function can be called out by its ANSI device code. This is just an arbitrary 2-digit number that represents a function or a device defined by ANSI and IEEE. I'll scroll the list on screen so you can see them all. There's also a link to the Wikipedia page in the video description as well. Honestly, I've been doing this for 12 years. I don't remember them all. I have to look this article up all the time to remember what's a 67, you know, what's this, what's that, what's a 47. Don't stress out about memorizing all of them. You don't need to memorize all of them. I just need you to know a couple very common key ones, and then anything else that comes up along the way, you can look up as you go. 52, ANSI device code 52 is an AC circuit breaker. It could be a big, giant, massive 500 kV SF6 circuit breaker out in a substation somewhere, or it could be a small 480 volt little molded case breaker. Just know that 52, ANSI device code 52 refers to the breaker itself. It's something that opens the circuit, usually has a protection function tied to it. ANSI device code 50 is an instantaneous overcurrent device. 51 is an inverse time overcurrent device, or like a thermal overload. 27, very common, that's under voltage. 59, slightly less common, is over voltage, which you see 27, 59 all over the place. We'll talk about them here for the 751. 81 is frequency, either over or under frequency. 87 is differential. Again, this is just the foundation. The numbers often have a suffix letter to help specify what the function is for. 52G is often the suffix given to generator breakers, for example. 52A indicates breaker status. So this is a signal from a 52, an AC circuit breaker, going to some other thing. It shows that the breaker is open or closed. So 52A is a logical 1, or the bit is high, or the circuit is energized when the breaker is closed, and it will be de-energized, held low, or a logical 0 when the breaker is open. 50N and 51N are really common ways to describe neutral overcurrent. 81O and 81U are often used. I actually don't call them out this way on the 751, but I do want to talk about it real quick. 81 is for frequency. 81O is often the quick hand that we use for describing over frequency, and 81U is for describing under frequency. 87T is a term generally used for transformer differential, and 87B, 87 is for differential, 87B would be for bus differential. You can see how these shorthand codes can be really helpful when programming and testing relays. You can summarize really complicated concepts and string together long Boolean logic equations in a standardized and almost readable way. Just don't feel like you have to try to remember them all at once. You can look it up on the Wikipedia page, you can look it up in the relay manual for whatever device you're working on, anytime that you're connected to the internet, basically, just like how you can support my channel for as little as $2 a month by clicking the join button down below anytime you're connected to the internet. Boom, segue. Let's look at a real example combining Boolean logic and some ANSI device codes in the trip equation in an actual SEL relay. So this is what it's going to look like in a program. This is the meat and potatoes of relay testing for technicians, right? First off, in SEL's language, whenever you see TR or trip, they're used interchangeably. That is just another digital Boolean variable or logic bit that's shorthand for the trip equation. We find that here in the settings, so under group 1 or whichever active group you're testing. We find that under trip and close logic. We'll see in a second where we plug in the trip word bit to make an output close and affect the physical system, but for now let's break down this equation. Let's find out what would cause trip to change from a 0 to a 1 in the first place. First, we see that there's 3 chunks, obviously, that are ORed together. Every time you see OR, that's another thing that can make it change state independently of everything else. 50P1T, this first part, is an overcurrent trip. The logic here, 50 is the ANSI device code for instantaneous overcurrent. P is for phase. The 1 is just element number 1. There's element 2, 3, 4. We can select up to 4 different instantaneous overcurrent elements on this relay. And then P, again, is the second P is the pickup. In this case, the bit that goes to the trip equation is T, 50P1T. When this instantaneous overcurrent element 1 picks up and times out, which you can add a delay, it's not really instantaneous at that point, it's convention. We do that because of convention, not because it's easy. It's Stone Age logic plugged into modern computers that can do way fancier shit. When 50P1P, instantaneous overcurrent element 1, picks up and times out, the bit 50P1T will go from a 0 to a 1, and then we plug that into our trip equation, 50P1T. If that goes to a 1, TR becomes a 1. That statement becomes true, and again, we can use TR elsewhere in the program. It just sums all of these protection functions together. We'll do a whole deep dive on how that works and how to test it in future videos. It's coming, but for right now, we're just talking about the logic. Again, if 50p1t came high and none of this other stuff changed, it would still engage that trip. It would still become true. The next thing in parallel to that is PB04. So what is PB04? Well, PB is just short for push button. In this case, it is, I'll show you on camera here, this trip push button right here. Please focus. There we go. This trip push button right here. If you push this trip button, it sends a trip to the breaker, right? So anytime this button is pressed, stop focusing. Anytime that button is pressed, the trip equation becomes true and will send a trip signal to the breaker. That one's pretty straightforward. Whenever the button isn't pressed, the PB04 bit is a 0. When the button is pressed, it's a 1, making the trip equation 0 to 1. Okay, let's look at this last chunk in parentheses here. Parentheses? Fuck. I don't get paid enough to know how to talk and test relays, all right? Fuck off. 27P1T and 52A are in parentheses. Now we'll break this down a little bit. Similar to 50P1T are 27P1T. Again, 27 is the ANSI device code for undervoltage, which we can see here in the settings. This one's set to 0.85, so 85% of our nominal voltage and half a second delay. If both of those are true, then 27P1T goes from a 0 to a 1. 27, ANSI device code for undervoltage. P is phase, so any phase having an undervoltage. 1 is just element 1. We can see here there's 2 undervoltage elements we can use. 27P1, undervoltage on the phase, element number 1, and then T is the trip. So when it times out, when this and this are true, then 27P1T goes from a 0 to a 1. However, if I don't have the other part of this equation, because it's an AND function in the parentheses, it won't make the whole trip equation go high. I need 27P1T and 52A. In this case, 52A, again, is the breaker status input. It follows the breaker. When the breaker is open, 52A is 0. When the breaker is closed, it's 1. Sidebar, if you ever see 52B, generally with a lowercase b, SEL logic, everything is caps lock, but generally 52A and B statuses, 52 with a lowercase a for the breaker status signal. 52B, if you ever see that, that's the opposite. So it's a 1 when the breaker is open and it's a 0 when the breaker is closed. 52A follows the status of the breaker. It's high when the breaker is closed. That's what we generally use just by convention, but there are reasons that you would need an affirmative open or an affirmative close. You would use both 52A and B. Anyway, circling back, this chunk over here, 27P1T and 52A, we need to have both the 27 element timed out and the breaker closed as indicated by the 52A signal. Both of these word bits need to be high or set to a logical state of 1 in order to make the trip equation go to 1. This is a pretty common thing in trip equations and relay programming. We don't generally want to hold the trip circuit closed or hold the trip circuit energized if there's an undervoltage, like just a bus outage, some normal thing, we just have it off, whatever. I don't need to hold the trip coil for the breaker energized. So you might see this a lot. So that's what we see here. We use programming logic to make the relay physically operate the system the way that we want. Knowing a few ANSI device codes and understanding the Boolean logic equation, we can set up pretty complex operations like this relatively quickly, and if you know a few things about how the relay works and how Boolean logic works and how the ANSI device codes relate to what the relay is actually looking for, we can look at this and know immediately what the relay is trying to do, and then it makes it easier to test it. So if we click down here under logic 1, we can see that we've got a couple other things here. And you might have also noticed here in our trip and close logic, I've got the input in 302 for my breaker status. And then under slot A, so like logic slot A, we've got out 101, out 102, whatever. The whole point of a protection relay is to monitor the condition of a power system and open a circuit breaker when something goes wrong. For digital signals like our 52A contact from the breaker, those are brought to hardwired points on the back of the relay. They look like this. These are the terminals that we're going to hardwire those electrical signals to. These generally make intuitive sense, I think, to a lot of people. When I have voltage across the terminals of input 302, that is seen as a high state. So the logic bit for in 302 goes from a 0 to a 1 when voltage is applied. If you take voltage away, that logic bit in 302 goes to 0, and it's held low until voltage is applied again. And in this case, our 52A status only follows that input 302. So we know that when I have voltage across in 302, my breaker is probably closed. That's what it's wired for. That's how the system is designed. 52A word bit or logic bit will go to state of 1. It will be high. And then we can use that for other things, just like we did in our trip equation. We used hardwired inputs from the system for a ton of different signals, from breaker control switches, breaker status inputs, push buttons, maintenance mode switches, lockout relays, PLC automation signals, other hardwired alarm contacts, some stuff like transformer oil temperature sensors. The list goes on. Almost anything the protection relay would want to know about that's a digital signal, on or off, we can wire straight into the back of the relay and then just use the logic bit name in 101, in 102, in 302, whatever. We can use that in the program in place of the physical thing. Similarly, when we go to the logic outputs, so on this I have to go to the logic subtab and then drop down to slot A or slot C, and these correlate to different output decks on the back of the relay. So slot A is going to be this top deck. Slot B is our COM card, so we don't have anything in there, but if we drop down to slot C, that's the second row of terminal blocks here, and they correlate to the names on the sticker on the side of the relay. It's really convenient. When a logic bit, out 301 for example, goes to the state of 1, so if we look at our example here, 50P1P. When 50P1P logic bit goes high, goes to a state of 1, out 301 will close. Generally, that is. Quick sidebar, this out 301 failsafe mode actually flips the state of this, and there's some other stuff that we're going to talk about in another video. Failsafe outputs are kind of a pain in the butt, but just know that it's when the relay's on and everything's working correctly, it's swapped. So it would be held low when the logic equation for the input of it is high. They're just reversed. 90% of the time, probably 95% of the time, everything you're going to see is the outputs are not in failsafe mode. Specifically for trip equations, they're almost never in failsafe mode because maybe you took it out for maintenance, you trip stuff. We don't want that. Nobody wants that. Nobody wants to have an unintended outage. You'll often see the trip variable thrown into one of the out logic equations, and it's important that you make sure that output is physically wired to the breaker trip circuit. When this output closes, as in the logic for output 301 is a logical 1, a physical contact inside the relay, inside here, closes and sends an electrical signal off to the trip circuit or to another alarm circuit or to a PLC or whatever. There is a physical contact in here that closes whenever it calls out 301, when that bit goes to a 1, when that logic equation becomes true, a physical contact in here closes, and that's how the relay interacts with the real world. The last thing I want to note for these SEL relays, the terminal names fuck people up all the time. One notable time I saw that actually made an entire power plant go dark for a few hours because someone installed a jumper in the wrong place. We got to really pay attention to how these work. On the 751 and many SEL relays, the top terminal deck has inputs and outputs labeled 100 something, so in 101, in 102, out 102. The terminal numbers start at A01 on the left and increment to the right, A02, A03, and so on all the way to A08. The second deck down has functions numbered 200, like in 201, out 203, whatever it is. and the terminal numbers are B01 through B12. What I'll warn you is that you don't want to get confused between out 101, which uses, in this case, terminals A03 and A04, with terminals number A01. So terminal A01 and out 101 are two different things in this case, because terminals A01 and A02 are for the power supply. So if you are wiring this up, you need to make sure that you're looking at the terminal numbers and not the functional name of the thing that you're trying to do. They're two different things, just be aware of that. It's really, really embarrassing when you fuck that up and turn the lights off. This video is long enough. Sorry for all the rants and sidebars. I'm calling it here. Be sure to check out SEL Logic Part 2 and the rest of the videos in the series in the playlist and linked in the description. Make sure you're subscribed. Do all the fun YouTube stuff. Leave a comment if you thought I said something stupid. And remember, if it ain't grounded, it's not dead. Stay safe and I'll see you in the next one. Thanks, guys.